Welcome to the fourth lecture in quantum field theory. Now we will begin studying the solutions of the Dirac equation, because what we had previously found is this expression right here, where this weird slash notation is simply going to be right if we have some A slash. This simply means gamma mu, the gamma matrices, d mu. If you don't know what these symbols are, then I recommend you go back to the first few lectures of this course, where we go a bit more into detail of where these gamma matrices come from and what this del mu notation is. Okay, so if this is the first time you see it, you will probably have to go back in this course a little bit more. All right, so what we now want to do is figure out what sort of particles are represented by this psi. Okay, so what sort of particles can we describe? What are the properties? What are the limitations of the Dirac equation? That's what we want to begin studying. So first, let's just look at the solutions themselves and try to figure out what form they have to have. Okay, so what we have right here, we can simply expand as I gamma mu, right? We are simply plugging the value for the derivative slash notation. Del mu minus m psi equal to 0. Now, keep in mind that this entire thing is 4 by 4, right? We have this implicit unitary 4 by 4 vector, right? The identity matrix. So, of course, if this is 4 by 4, then this thing here, we would want it to be 4-dimensional. Okay, so our psi will now no longer be simply some scalar amount. It will now be a column vector of 4 dimensions. So it's going to have some component here in the first coordinate, some here, and some here. Okay, so it's going to have 4 coordinates. I'm simply going to call them 1, 2, 3, 4, not particularly creative. And what exactly are they going to be? So let's do what we usually do and think of plane wave solutions. Okay, that's just the classic trick that, or rather just the procedure that we like in quantum mechanics. So each one of these psi alpha, with alpha being 1, 2, 3, 4, is going to be the plane wave part, so e to the minus I px, and then we multiply by u alpha of p. So u here, this is simply going to be some constant, or rather some component that may depend on momentum, some expression that we don't really know what it is just yet. And eventually we are going to want to normalize this. Okay, so we are going to want to normalize these u's. So for now, we are simply allowing for there to be some extra factors, right? So that's why we are putting that u there. And of course, the alpha is because we have 4 possibilities. So basically, each one of these will be e to the minus I px times u alpha, or rather, sorry, we have to plug in the actual value. So u1 of p, u2 of p, u3 of p, u4 of p. So in this notation, we could also just call this e to the minus I px u of p, right? This is just some notation. Okay, so now that we have this, let's actually plug it in to our initial expression, or rather actually to this one right there. So we have I gamma mu, and now we want to apply this derivative operator onto psi. Now del mu is the same as d dx with the mu up here, and psi is e to the minus I px, but we can write this just to make this a bit easier to see how we have to take this derivative as p mu x mu. And then we have, well, of course, still the u term, so up, and then minus m times e to the minus I px. I'll just leave it like this because, well, we don't have any reason to write it down explicitly. Up, and all of this is equal to 0. So here we apply the derivative. So we get I gamma mu, and from this derivative, we get minus I p mu. And then we still have the exponents, but now we can factor the wave function out. So we can factor this and this, right? So we get this minus m times e to the minus I p mu x mu u p. I guess I didn't have to write down the mu's here, but well, I did it. Okay, so now for this to be 0, first of all, this part right here can't really be 0. So we can just drop it for now and stick to the rest. So here multiplying through, we get a minus sign from the I squares, and it will cancel out that minus sign. So we get gamma mu, p mu, minus m, and this times u of p. Okay, so now for us to go ahead, we will do a little bit of a simplification just to make the calculations easier. We could not do it, but things would be much harder, and we can then go back and undo this simplification to find the general solution. So what we will do is say that our particle, or rather we will choose a coordinate system where our particle is going in a single direction, right? We can always do that. If our particle is going in any direction, we can always choose a coordinate system where it is going in any particular direction, right? We can put one of your axes in the direction of movement. So what we can do, we will say that P1 is going to be 0, and P2 is also going to be 0, which means that only P3 will be different than 0. So this is basically saying our particle is moving in the z direction, okay? All right, because keep in mind, P1 corresponds to Px, P2 corresponds to Py, and P3 to Pz. Okay, even though we don't use those names, but that's basically what's going on. So now let's multiply through there in that product. So there we would have gamma 0, P0 plus gamma 1, P1, right? Keep in mind, this has an implicit summation, right? We said that whenever we have something like this, we are implying that there is a sum from mu equals 0 to 3, right? But since we are going to encounter this so often, we use Einstein's convention, and that is that we just don't write the summation, okay? But you have to keep in mind there is an implicit summation. So this is the multiplication of these, but going through every single one of those indices. So that's why we're doing this. Okay, and that's incredibly important for you to know. Okay, and then minus m, and all of this times u of p. But of course, P2 and P1 are equal to 0, so goodbye to these friends there. Okay, so we are simply left with this thing right there. So let's move it there. Okay, so now what we want to do is just choose some convention for our gamma matrices. Okay, so let's write down our gamma matrices explicitly. Now here you can use whatever convention you like best. So you could just use whatever one you have seen in class or whatever. I will use the one that I like best, but the physics is completely independent of which representation you use. Okay, so sure, the intermediate steps can be a little bit different, but the end result will be the same. So I will use the Pauli-Dirac representation of the matrices, a representation of gamma matrix. And in this representation, we have that gamma 0 is going to be the unitary matrix 0, 0 minus the unitary matrix, and each one of the gamma i's is simply 0, sigma here of course being the Pauli matrices, sigma I. So this means that gamma 3, right, gamma 3 would simply be 0, and now sigma I, this would be sigma 3 minus sigma 3, 0. Okay, but what exactly are those sigma 3's? Well, the Pauli matrices, right, the third, oh sorry, this is supposed to be here, the third Pauli matrix, this is simply 1, 0, 0, minus 1. So here we have 0, 0, 0, 0, and then we have minus 1, 0, 0, 1, and a bunch of zeros. Okay, so this is what we have. All right. And well, just to keep in mind, each one of those here, just to make it very clear, and there as well, and there as well, all of those are 2 by 2 blocks. That's why we end up with a 4 by 4 matrix. Okay, so let's plug this into our blue equation. So gamma 0 P0 is simply going to be P0, 0, 0, P0, then 4 more zeros, 4 more zeros, and then minus P0, 0, minus P0, sorry, that's a 0 there, minus P0 there. Okay, so that's gamma 0 P0. like this. So this is gamma 0, P0. There. Then we have to add gamma 3, P3. So now comes gamma 3, P3. So this would be 0, 0, 0, 0 minus P3, 0, P3, P3, 0, 0 minus P3, 0, 0, 0, 0. And then we have minus M times the 4x4 identity matrix. Don't forget about that. So minus, or rather, let's do it like this. Plus minus M 0, 0, 0, minus M 0, 0, 0, minus M 0, 0, 0, 0, 0, 0, minus M. And all of this, right, the sum of all of this is multiplied by U1, U2, U3, U4. And this has to be equal to 0. Okay, so now we have this little beautiful matrix equation. Okay, so let's just add these matrices together to see what we end up with. So we have, in the diagonal, we have P0 minus M. Then we go down one step and we have 0. Then we go down another step and we get minus P3, 0. Then we get P3 here, 0 here. Then in the next step in the diagonal, we also get P0 minus M, 0. Then here we have P3, 0, 0 minus P3. Then in the next one in the diagonal, we have minus P0 plus M, right? Both of them are negative, so we can factor out a minus sign. And then 0, 0, and another minus P0 plus M. And all of this multiplied by U1, U2, U3, U4. Of course, all of them have a P dependence that I'm not always going to write because it's a little bit annoying. Okay, so now what we can do is multiply through. Okay, so let's multiply through and just get our equations explicitly. So multiplying this first part, so right, that, we get P0 minus M, so P0 minus M times U1 of P, and then we get 0 times U2 plus P3 times U3 of P, and well, 0 times U4, and this is equal to 0. Then we get, in the next one, 0 times U1, we get P0 minus M times U2 minus P3 U4. And that's equal to 0. Now we go to the third equation where we have minus P3 U1, and then we have 0 times U2 and minus P0 plus M times U3 of P is equal to 0. And finally, in the last equation, we have 0 times U1, P3 times U2, and then 0 times U3 and minus P0 plus M times U4. Okay. So now, look at what we have. So we have P0 minus M, P0 minus M, U1, U2. P3 minus P3, U3, U4. Minus P3, P3, U1, U2. Minus P0 plus M, minus P0 plus M, U3, U4. So we have these little groupings of U1, U2, U3, U4, right? You can see that U1 and U2 are always kind of together, and P3 and U3 always are kind of in the same situation. So this invites the notation. Of course, this is a little bit of a stretch, so don't worry if you hadn't thought of this. This invites the notation of grouping U1 and U2 into a new vector. So we can say U tilde of P is going to be U1, U2 of P. Right, so just this two column vector. And then we have V tilde of P, which is going to be U3, U4 of P. And this will allow us to simplify our notation and make solving this easier. Okay, so what we'll do here now, by the way, just to make very clear what's going on, this means that our U of P is going to be U hat of P, V, not hat rather, but tilde, sorry, v tilde of p. Okay, so if you plug those in, you can see that we are still in the same spot as before. So how do we use this to simplify this equation? So notice we have p0 minus m, p0 minus m. So basically if we had p0 minus m times u tilde of p, right, this, if you multiply through, you end up with precisely what we have right there. Okay, so that is the same thing. Then we have p3 and minus p3. Okay, so that part is a little bit more difficult. So because one of them is positive and one of them is negative. Well, where have we seen something that is two-dimensional and has a positive and a negative sign, and is kind of something that is like unity, right? Something like this. So basically, what we want to use here is the third Pauli matrix. So sigma 3, we know that this is 1, 0, 0, minus 1. So if we multiply this times p3, right, sigma 3 p3, this is 1, 0, sorry, or rather p3, this is p3, 0, 0, minus p3. And if you multiply this thing by, okay, so I need some more space actually. So let's now multiply this. So sigma 3 p3 times u1, u3 u4 is what I have to multiply it by. So multiply by u3 u4, we end up with, take a look at this, p3 u3 and minus p3 u4. Okay, and look at this, it's exactly what we had before. So we can write this little block here simply as plus sigma 3 p3, and now we multiply by this u3 u4, which is what we called v tilde of p. Okay, so now in this little concise equation, we have written all the information that is in these two equations, right? So you can see that we have simplified this quite a little bit. And now we can do the same thing down here, but notice that here we have the minus changed, right? So that would be minus sigma 3 p3 u tilde of p, right? If you multiply this explicitly, we have minus 1, 0, 0, minus 1 times p3. Well, I guess we can just write the p3 in there right away. So this is p3, 0, 0, minus p3 times u1, u2. So this would give us minus p3 u1, and then down here we would get plus p3 u2, which is exactly what we have up there. Okay, so just making sure that this is indeed correct and that you guys are following me. Then we have this one. Well, this is easy. So this is simply p0 plus m factor of v tilde. Right, and again, you can just multiply through and corroborate if any of this didn't make all that much sense to you. But now we went from 4 equations to 2 equations. Of course, these equations have implicit equations in them, but that's going to make it easier to solve. So now let's go to a particular case, because we know, right, as we saw in the previous lectures, that the energy, in this case, the energy for the Dirac particle can be either plus or minus the square root of the momentum squared, but in this case we only have the momentum in the z direction, so it's only going to be p3 squared plus m squared. All right, so we have 2 possibilities. You can have positive energies and negative energies. Okay, so let's for now just go for the case of the positive energy, so E plus, right? So that would of course simply be the square root of p3 squared plus m squared. Okay, so let's see what happens in this case. Of course, we are going to go to the other case once we are done with this, so don't worry, you can start with whichever one you want. And now let's go to these equations and solve for either u of p or v of p and just see what happens. Now, it doesn't really matter which one you go for. You can go for any of the 2 equations. I mean, from which equation you solve them, of course. It does matter if you solve for u or v. Because if we solve, let's say that we choose this equation, right, which is what I will do. If we are in momentum equal to 0, then this entire part is 0, which forces P0 plus m times V hat of P, this to be equal to 0, right? So if P3 is 0, it forces V tilde to be 0. All right, so that means that V tilde is dependent basically on the other part, while U tilde is not dependent. So that is why we will solve for V tilde, because that is the dependent part. Okay, so going from this equation, we get that V tilde of P is going to be, let's see, so we get a minus sigma 3 P3 U tilde of P divided by P0. But what is P0? P0 is the energy, right? So it is basically what we have right there. That thing is P0. So it's simply going to be E plus. So divided by E plus M. All right, so that is our V tilde of P. Now, our U tildes, this is this two-dimensional column vector. So we can choose it freely, because we are going to have to normalize this wave function later, and we can reduce this to just the possible vectors that span this space. So there are two possible U tildes that we could go for. We could go for 1, 0 or 0, 1, right? Every other vector is simply going to be a linear combination of these vectors. So there are two possible values thus for V tilde of P. So V tilde of P can be in the case where we have this one, which I will call, for no particular reason, with this arrow upwards, kind of like spin up, but we haven't said anything about the spin of the particle, so I'm just going to use the notation and it will make more sense later. So this is minus sigma 3 P3 E plus m, and then 1, 0. And if we multiply through, keep in mind that this is the matrix 1, 0, 0, minus 1. So what this is going to do is that once we multiply through, we have minus P3 divided by E plus m in this part, and of course 0 down here. So the sigma 3 didn't really change anything, because we are multiplying 1, 0, 0, minus 1 with 1, 0. So this simply gives us 1, 0. Okay, but in the other case, where we are in this other, so when we are with the arrow down, right? So the arrow down, this one right there, we would have minus sigma 3 P3 E plus m, and now we have this 0, 1 vector. And here we multiply through, but now we have 1, 0, 0, minus 1 times 0, 1, which gives us 0, minus 1. So there will be a minus sign here that will cancel out this minus sign. So we end up with P3 divided by E plus m. Wait, sorry, I need to make some room. This is too chaotic. Okay, now, so this will be 0 and then P3 E plus m. All right, so those are the two cases here that are linked to the case where the energy is positive. So just plugging all of this into our U, right? And just to keep in mind, what is everything? U that we are going to find now is this, right? U of P, which constitutes our wave function. So once we know U, we basically know the wave function, right? So once we know U, we know the wave function. We only need to multiply by e to the minus px. Okay, so our U of P for the positive case, right? There are going to be two possibilities. One will be when you have this up sign, which doesn't have much more meaning now. It will be related to the spin of the particle. This will be the up case because the spin is going to be 1/2, but we don't know any of that yet, so don't let me spoil it, even though I already did. So this we know was U tilde of P, V tilde of P. So what is U tilde? Well, in the up case, U tilde we said is 1, 0. And V tilde, we just saw, is going to be minus P3 E plus m 0. All right, so that is one case. And then we have the possibility u plus down, right, with the minus 1/2. Again, that's spoiling, but it's just so that you can kind of see where this is going for, or going towards. And here we have, again, u tilde, but u tilde this time is 0, 1, and then v tilde 0, and p3 e plus m. Okay, so this is what our wave function looks like in this particular case. Now let's go for when the energy is negative. If the energy is negative, right, so then we would be in the case where the energy is minus the square root of p3 squared plus m squared. And this, of course, would be p0. And we can just call this E minus. Okay. So in this case, our equations, they don't really change. In fact, maybe I'll just take this and take it with me because I don't really feel like writing it down again. So what we did previously is that we used the second equation to find our conditions. Let's now go for the first one. Again, which one you use doesn't really make sense in the end. I mean, sorry, it doesn't make any difference. But I just like to follow the convention so that our results end up being the same that most books tend to use. Okay, so now going for the first one, we can see that in the first equation, it is V that is going to be independent, because if P3 is 0, if we are not moving at all, then U has to be 0. Okay, so in this case, U is going to be the dependent part. And by the way, you can also see quite easily that this condition did hold previously, right? We said the same here. If P3 is 0, then V tilde, which is this part, is 0, right? Because P3 is 0. Okay, so that condition did hold before, just making sure that everything is making sense. Okay, so from here, we can solve for U tilde. So U tilde, which is the dependent part, will be sigma 3, or rather minus sigma 3 P3 V tilde of P, and then we have P0 minus M. Of course, P0 this time is going to be E minus, so E minus. Okay, so just like before, we have two possibilities for our V hat, right? Because it is two-dimensional, we can go for 1, 0, or we can go for 0, 1, and that will cover every possible solution. So let's take a look at each one of them. We will go for U hat. This is minus, by the way, because it's the minus case, so negative energy, but up sign, so we will go for 1, 0. Here we have minus. Now, sigma 3 times 1, 0 will simply give us 1, 0. So this will be minus P3 divided by E minus minus M 0, right? I just multiplied through right away. And then we have U minus down sign, which will be, and now this will give us 0 minus 1, right? So when we multiply through, we get 0, and then P3 E minus minus M. Okay, so using this, we can, just like before, construct these U solutions. So U, not anymore U tilde, just U. This will be U minus in the up case. This will be minus P3 E minus minus M 0, and then 1, 0. And then in the other case, so U minus down, this will be 0, P3 E minus minus M, and then we have 0, 1. So these are both of our possible solutions. So now we know, right, that if we have positive energies, or if we want to look at the positive energies, then we need to use this wave function if it is spin up, even though we haven't really talked about the spin, so we are speculating for now. I will give you the proof in another lecture. This will be in the case for negative energies, and spin down, positive energy is that, negative energy is that. So we only have to choose the correct one here and then plug it into this part, which is the wave function, right? We said this is going to be our psi, right? So we simply plug it in there, and there we go. That is going to be our wave function for the Dirac equation. Now let's go ahead and try to find a bit of a more general expression, right? We don't really have to or want to write down like 4 expressions every single time. And also let's try to see what happens if we are not traveling just in the z direction, but in a more general direction. So in that case, let's begin first by trying to write these in a bit of a more compact form. So u plus of p, right? Now we haven't gone, this is still in P3. We are just going to combine these 2 expressions, and then we're going to go a bit deeper. So this is u tilde of p, and we know the expression for v of p, right? We're going to write the expression for v of p, which is exactly this. So it is minus sigma 3 p3, right? So it is minus sigma 3 p3 divided by e plus m times u tilde of p. All right, so here we can see that we have implicitly the up and down cases. So if we are in the up case, then we take u of p to be 1, 0. But if we are in the down case, then we take it to be 0, 1, and we will get to the same results that we previously had. So this is the same, but more compactly. And similarly, for the negative energy cases, we will have minus sigma 3 p3 e minus m times v hat of p and v tilde, tilde, not hat, of p. Okay, so this also is now in a more compact notation. But we can do better because this still has e plus and e minus. But in reality, we can combine those expressions because we know that e plus is equal to e and e minus is equal to minus e. So we can plug those things in. So e minus here will simply be minus e, and e plus will simply be e, right? Whatever the energy is. So we can factor out a minus sign here, which will cancel out that minus sign. So we get sigma 3p3 e plus m, and we have this minus sigma 3p3 up there. Now, to generalize this into 3 dimensions, what we can do is keep in mind that if we have some pi, we can always raise the index as pi, but adding this minus sign in front, right? As we discussed in the first lecture. So now what we will do is simply go from this sigma 3 to just a general sigma I, and p will go from just overall from p3 to an overall pi, right? So we will have to raise the index on the pi's just to make sure that we are going to cover every case, and just apply this dot product. So this negative sign will be cancelled out, and we get now the dot product between the sigma vectors, right? Sigma 1, sigma 2, sigma 3 times p1, p2, p3. All right, so in the third case, we would get minus sigma 3 p3, which is exactly what we have here. And in this case, we need to add a minus sign, so we get minus sigma dot p. All right, so there it is in a much more general notation. So that is it for the wave functions themselves. With this, they are completely determined once we know the direction, right? We can see if we want to study up or down cases, positive or negative energies. We will go into thinking about the negative energy part very soon because it is weird, right? Allowing for negative energy states, that's weird. But don't worry, in a few lectures, we will go in depth into that and see what's going on. But for now, let's go ahead and try to normalize these wave functions, okay? So now what we want to do is to normalize our wave function, right? We wrote it down as e to the minus ipx up. So now we want to normalize it. Of course, to normalize it, we need to integrate over all of space. Now we are in 3 dimensions, so I will write it as d3x, right? That's just general notation, right? We are integrating in 3 dimensions. We haven't chosen whether it's going to be cylindrical or Cartesian or spherical. We don't know, we don't care. This is a general notation. Okay, and to do it, we need, of course, or we can try, as usual, to go for the Hermitian. In this case, of course, we are working with matrices, so we have to be very careful that we also transpose it, and we'll have this for our wave function here, psi conjugate of p, and this depends on x, and then e to the I px times psi of p, and now we will allow for the possibility for the momenta here to have a different value, and we will of course see that it will force us that they have to be the same, but we are going to keep this general. Okay, so this is the expression that we want to normalize. We can now see, of course, that the exponents, what we have here, this is p prime, so this of course is also p prime. So we get integral d3x of e to the ix p minus p prime, and we still need to multiply by u Hermitian of p times u of p prime. Okay, so now what we see is that this integral right there is precisely, or almost rather, the definition of the Dirac delta. So the Dirac delta in integral form is 1 over 2 pi times the integral of dx, right? This is in one dimension, e to the ix p minus p prime, right? So this is almost the same. We need to multiply by 2 pi. So we see that the integral that we have there is 2 pi times the Dirac delta for a given direction. We have 3 directions, so basically what we have is the 3-dimensional Dirac delta, right? It goes for x, y, and z. You have to have the same momentum in each direction for this to be not 0. And then we have 2 pi cubed, right? We have this 3 times, they multiply, it becomes cubed. And that means that our u's will now be dependent on the same momentum, which is of course what we wanted. Okay, so now what we need is to see what's going on with this thing right here, right? Because we would love for this entire thing to be normalized. So what exactly is going on here? Is this going to be 1? Let's see. So of course, what we want is for this to be normalized. Usually we say this has to be equal to 1, but that is not necessarily going to be true in this case, because now we are going to be working in Lorentz invariance. We want things to be Lorentz invariant, and saying that this is equal to 1, well, it's not particularly Lorentz invariant, as we will see in the lectures where we go full in depth into Lorentz invariance. So for now, we will say this is equal to, and just leave it there. And we will continue exploring this. So of course, what is this product? So U Hermitian of P U P. Now we know that there are 2 cases. So case where energy is positive. So that means that we are going to be working with the plus versions here. Okay, so what exactly are those? Well, let's write it down somewhere else. So we have seen, well, actually we have seen that they are like this. Okay, so let's now allow for the possibility of these normalization constants. So let's say that we can have a normalization constant here that's going to be maybe alpha here and beta right there. Okay, so that's going to be the normalization constants that we work with. So let's plug that in. So U Hermitian plus, right, the positive energy cases, right, in the Hermitian one. So this is going to be, let's see. So this would be alpha, which is of course outside of the matrix. We have alpha conjugate, right? Alpha is simply a scalar, so we can just write it like that. And then we have, this is going to be now transposed. So this will be U hat Hermitian of P. And then we have U Hermitian of P sigma dot P E plus M. Keep in mind that when you take the Hermitian adjoint, you have to also order change the order, right? So this one, which used to be there, is now in the front. And you can't just change the order whenever you want. Things don't always commute. So we can no longer just rearrange whenever we want, unless we are sure that what we're dealing with commutes. Okay, so this is U Hermitian. Now we go for U, so that's going to be alpha and what we have already seen many times before, so U tilde of P, sigma P E plus M, and U tilde of P. Okay, so now we just multiply through. So multiplying through, we get, well, alpha conjugate alpha, which is simply the modulus of alpha squared. Then we have U tilde Hermitian conjugate here, P times U tilde of P. And then we have plus U, oh, I missed the tilde there, sorry. U tilde there times sigma dot P times sigma dot P divided by E plus M squared. And then we have U tilde of P. Now, as you may recall from quantum mechanics courses, there is an interesting property or a useful property for the sigma matrices. If we have sigma A, sigma B, this is A dot B plus I sigma dot A cross B. We could prove this at some point, but honestly, I think it's a little bit beyond the point. If you're really interested, I can make a video about it. But it's just one of the general properties of the Pauli matrices, so I don't know if we are all that interested in it for now, but if you are, let me know. Okay, so using this, but for sigma p, we get that sigma p is equal to p squared plus I sigma dot p cross p. Of course, p and p are the same, so the cross product will be 0. So we end up with simply p squared. All right, so plugging it in, we have alpha squared, and then this thing right there. So we want it to be 1 if this is normalized, or 0, 1 if we are in spin up, right? If both of them are spin up, then we want it to be 1. If both of them are spin 0, we want it to be 0, right? After all, in this notation, we said, okay, so U hat, it could be 1, 0, or 0, 1, and they're always going to be the same choice. So you will either have 1, 0, 1, 0, which is 1, or you will have 0, 1, 0, 1, which is also 1, or you can have any mix like 0, 1, 1, 0, which would be 0, or the other way around. So the point is that we will keep it in this explicit form, or rather with the current notation, just to make sure to emphasize that it's either 1 or 0, right? Depending on which case we are. If they have the same spin, then it's going to be 1. If they have different spins, it's going to be 0. Okay, so this is U tilde P blah blah blah, U tilde of P plus, and now P squared is simply going to be a scalar. We can commute it, so P squared, and then U tilde here. So we can now factor this out. So we can factor it out. So this thing here will be 1. And there we go. And this is, of course, divided by E plus M squared now. Okay, I almost forgot about it. All right. So now let's just simplify this a little bit. Let's take minimum common denominator here. So we get E plus M squared plus P squared divided by E plus M squared times our beautiful U's. All right. And here, let's see, we have still our alpha squared, and we can now expand this. So we get E squared plus 2ME plus M squared plus, and momentum squared, we know that the energy is going to be equal to P squared plus M squared, which means that P squared is E squared minus M squared. Okay, so using this, we get E squared minus M squared times our U's. Okay. And all of this divided by E plus M squared. All right, So here we can simplify things a little bit. We can factor out 2e because these ones cancel out. So we have 2e factor of e plus m divided by e plus m squared. So of course, one of the e plus m's will cancel out. So we end up with 2e divided by e plus m times, of course, this quantity right there. Okay, so this is what we get for u plus, this is Hermitian of p, u plus of p, okay? So this is the normalization condition here. We still don't know exactly what this thing here is going to be, and I will tell you that in a little bit. First, we need to do now the exact same procedure, but for u minus and for, well, and u minus, right? So the exact same thing, but for u minus. But notice that, let's see, where is our u minus? Okay, so this is the expression for u minus. So the only difference is now, well, of course, instead of u, we have v tilde, and we have this minus sign. But when we multiply it with itself, the minus sign will cancel out. So other than that, it's the exact same expression, but with v's instead of u's. So for that reason, it really makes no real sense to worry too much about solving it again. I mean, you can do it, but it's the exact same procedure, instead that it now has betas instead of alphas. So it has beta squared, but you will still get 2e, e plus m, v tilde conjugate p, v conjugate p. Okay, so these are those two results that we will get. Now, what may be a naive attempt would be to say, okay, we know that this should be equal to 1, right? And we could use that to find what the alphas and betas need to be. However, that would not be relativistic. For something to be Lorentz invariant, as we will see very shortly, this normalization would simply not work. So what we would have to do is that instead, again, this is something I'm just going to tell you now, and when we do the lecture on Lorentz invariance, we will learn more about this. But the actual normalization that we now need to do is normalize to E over m, right, to the energy. And in the case, notice this, if the mass or the particle is at rest such that the energy is equal to the mass, then it reduces down to the case where we are simply normalizing to 1, which is very interesting, right? When we go out of the relativistic case, we will go back to the usual normalization where we are simply going to 1. Okay, so if we do this, right, if we normalize to E over m, we can begin with the plus case. So in that case, we have that alpha squared 2e, e plus m, and now I will use the fact that these things are 1 if the spin is the same, or 0 if it's different. So of course, we will only have a meaningful result if the spins are the same. So we will simply use this as 1. And this is to be equal to E over m. So the e's cancel out, and we get that alpha squared is going to be E plus m divided by 2m, and then we take the square root. And then we do the exact same thing for beta, and it's the exact same expression, so we get the exact same result. So for beta, our normalization constant here will be the exact same one. Right, so using this, we can now simply go back to our initial case and see that u plus, the condition that we have found is that u plus has to be equal to, well, this would be E plus m over 2m u tilde of p sigma dot p u tilde of p divided by E plus m. And for the negative energy case, we would have, well, the same constant in front, so E plus m divided by 2m, but then we have minus sigma dot p. This is, of course, vectorial, all of it, so let's not forget about it. And then v tilde of p divided by E plus m, v tilde of p. Now, notice something that is quite interesting, that from the way that we constructed our solutions, we have that the product between positive and negative energy states is going to be the following. So if we have the plus case, right, and we multiply by the minus case, of course, we need to take the Hermitian adjoint to do this. Otherwise, the matrix multiplication is not going to make much sense. In this case, this would be alpha conjugate beta, right? So alpha conjugate coming from this, beta coming from that. And now let's write down a U plus Hermitian, which is U tilde Hermitian P, U tilde Hermitian P times sigma dot P E plus M. And then we multiply this by minus sigma dot P V tilde of P divided by E plus M V tilde dot P. All right, so if we multiply this, we get alpha conjugate P. Then we have U tilde Hermitian of P, and then times a minus sigma dot P divided by E plus M V tilde of P. And then we have the second part, which will be plus U tilde P sigma dot P E plus M V tilde of P. And notice that these are the exact same thing, but with a minus sign, so we get 0. So we can see that positive energy and negative energy solutions to the Dirac equations have 0 and are orthogonal. Now, do notice that the normalization that we used here, like this entire process, becomes meaningless for massless particles, right? So we cannot really try to describe massless particles with what we have done so far and with this Dirac equation, because notice this, right? If the mass is 0, then yeah, this just doesn't make sense. So if we want to describe massless particles, what we need to do is normalize not to E over M, but rather simply to E. Okay, so that's just, so we keep that in mind. All right, so there we go. We have understood a little bit better the normalization process for the Dirac equation. Of course, there still remains a little bit to be seen, because as we saw, we still have, what we basically found is this part right there, but the entirety of this product still has a little bit of a component missing, which will come a little bit later. But for now, we understood how to normalize the U solutions, right? U Hermitian and just regular U, depending on which energy case we are in. And that's going to be good enough for what we want to do now, because in the next video, we will study what the spin of the particle is. We will try to figure out how the physics of this problem will tell us what the spin is, even though we have already seen a lot of suggestions that it may be spin 1/2. But we'll have to wait for the next lecture in order for us to know for sure. So there we go. I hope that you have enjoyed this lecture. If you did, please make sure to leave a like on the video, comment, and subscribe, and maybe even consider checking out my Patreon. So I'll see you on the next video. Thank you very much for watching.